Welcome to today's lesson. Today we are on Unit 2, Lesson 2, which is all about the product rule. Let's first take a look at this example. Let's say, for instance, you have f of x is equal to x to the exponent 5 and g of x is equal to x to the exponent 7. Okay, so I want you to try this on your own. Okay, so pause the video right now and actually try this. So try first finding f primed at x and then g primed at x and multiplying them together. Then multiply them together and find dy by dx. Well, did you try it? And what did you get? Okay, well, let's do it together. Let's first do f primed at x times g primed at x. So let's do them separately. X primed at x will then just be 5, x to the exponent 4. G primed at x is then 7, x to the exponent 6. Okay, now we're going to multiply them together, okay, which would give us 35 x to the exponent 10. Is that what you got? Okay. Now let's do d by dx. Let's multiply the functions together first. So f at x times g at x, and then we'll find the derivative. Okay, so first we will find the multiplication of both, which is x to the exponent 12. Okay, so dy by dx then is equal to 12 to the exponent 11. Okay, so they do not equal. They do not equal. All right, so that's an important point to remember, that you can't just simply do this. Okay, there are rules when you have two functions. In this case, we had two power functions, but we're going to take a look at even harder functions than that are multiplied to each other and to make one single function. And the rules that we're going to need to apply in order to differentiate something like that. First off, let's take a look at something called the product rule. So if p of x is equal to f at x and g at x times g at x, where f at x and g at x are differentiable functions, so they are separate functions, and p of x is the multiplication or product of the two, then p primed at x is equal to the derivative of f at x times g at x plus f at x times the derivative of g at x. Okay, so the derivative of the first times the second plus the first times the derivative of the second. And we'll go through some examples. Okay, so let's take a look at our first example in which we had already sort of looked at and did our investigation on, but let's take a look at it a little bit further and apply our new product rule. So example number 1, okay, at first I'm going to do this the long way, and eventually you'll be able to just do this straight off the bat, but at first I'm going to actually specify this f at x and of course g at x. Okay, this helps me usually. F at x we said was x to the exponent 5, x to the exponent 7. Then we're going to say f primed at x is equal to 5x to the exponent 4. G primed at x is equal to 7x to the exponent 6. Okay, now remember that p of x, okay, is the derivative of the first times the second. Okay, so 5x to the exponent 4 times x to the exponent 7 plus the first times the derivative of the second. So x to the exponent 5 times 7 x to the exponent 6. Okay, so let's simplify that. So p primed, by the way, p primed then is equal to 5x to the exponent 11 plus 7, coefficients always come out front, x to the exponent 11. Okay, so that just works out to be 12 x to the exponent 11. Okay, all I did here was just collect like terms and simplify. Okay, and that would be our final answer right there. That we used. Looking at example number 2, we're going to use the product rule to differentiate the following function. F of x is equal to 5x plus 2, 8x minus 6. Okay, so we're going to use the product rule. So I'm going to do it the long way. Okay, I know this says f at x, but over here, maybe we can use g at x and h at x. Okay, so g at x will be our first function. Okay, and I always recognize using the product rule because they're, well, the product or multiplication of two functions. Okay, then h at x is equal to 8x minus 6. Okay, I'm just going to slide this over. G prime at x then is equal to 5x. H prime at x is equal to 8, and that's just 5. Okay, so it's just 8. Okay, so putting it all together in order to find f prime at x, it's the derivative of the first, and in this case, when you're using the product rule, the order doesn't matter because it's the sum of the two. However, if you want to keep track right now, that's fine, but it really doesn't matter the order, okay, because it is an addition. Okay, 5 times 8x minus 6, okay, and again it's plus. Let's move that down, and it's plus 8 times 5x plus 2. Okay, so working that out even further, it works out to be 40x minus 30 plus 40x plus 16. Okay, so we've got 40, 30, 40, plus 16. Okay, now collecting like terms, okay, 80x minus, okay, and that gives us f primed at x. Okay, that's our derivative. So let's move into something a little bit harder. Okay, this is actually example number 3. So I just want to go ahead and change that so it doesn't get confusing for you. Okay, so example number 3. Consider the function y is equal to the third root of x times x minus 2. So differentiate and simplify. So here I've just rewritten the function. Okay, so you'll notice that you've got two functions again, okay, that are multiplied to each other. And sometimes I even ask my students to label them if they really want to, okay, just so that they can recognize that there are two functions there and we can use the product rule. Okay, so I'm going to continue on for today, just using the same method, okay, is equal to, I'm going to change my third root to be x to the exponent 1 over 3, okay. F primed at x then is equal to 1 over 3 x to the negative 2 over 3. Okay, remember it's 1 over 3 minus 1. G at x is equal to x minus 1. G primed at x is equal to just 1. Okay, so applying my product rule, dy by dx, okay, is equal to x to the 1 over 3, okay, times, or sorry, plus this times this, which is, and again, notice I've sort of just gone in a different order, but that's okay. So what we have here is 1 over 3. I might keep my brackets just for the sake of it. Okay. X minus 1. Okay, so here we are going to simplify. X to the exponent 1 over 3. For now, I'm just going to leave my everything in exponential form. Okay, and I'm going to multiply this with each term in this bracket. it is going to get sloppy, and normally in calculus it usually does. Okay, so 1 over 3. So remember, when you're multiplying exponents of the same base, you're going to add the exponent. So negative 2 over 3 plus 1, which is 3 over 3. So we have 1/3. Okay, positive 1/3. X to the positive 1 over 3 minus 1 over 3 x to the negative 2 over 3. Okay, so basically it's just this times negative 1. Okay, so first thing I'm going to do is change everything over to a positive exponent, and then we'll take a look at the fractional exponents in just a bit. Minus 1 over 3x to the 2 over 3. Okay, all right. Now, let's see. We could add these two because they both have the same exponent. Okay, so 1 and 1/3. Okay, is the same thing as saying 4 over 3x to the exponent 1 over 3 minus 1 over 3x to the 2 over 3. Okay, so I lied. The next line I will now look at the fractional exponents. So 4 over 3, the third root of x, okay, minus 1 over 3 and the third root of x squared. Is there anything that I can possibly do now? The only other thing I could do in this case is to come up with a common denominator and add the numerator. But for now, I think I'm just going to leave you with that because we have everything in radical form as well as positive exponents. Example for today. We are asked to find the equation of the tangent line to the curve at the point 1 and 4. So our function is y is equal to x plus the square root of x times x squared plus 1 over x. So in example number 4, we want to find the equation of the tangent. So what we're looking for is y is equal to mx plus b. Okay, we want to find m and we want to find b. Remember that m is the slope, okay, which means it is dy by dx at that point. Okay, so the first thing we're going to do is actually find the derivative of our function. And I'm just going to quickly label this. You don't have to do this, but if it helps you for now, you can go right ahead and label that as f and that as g. So f of x over here, I'm going to change the first bracket here. You'll see that there is a radical there, so I'll just say x plus x to the exponent 1/2. F primed at x is then equal to 1 plus 1/2 x to the negative 1/2. Okay, g at x then is equal to x squared, and I'm going to change 1 over x to be x to the negative 1. Okay, so g primed at x then is equal to 2x minus x to the negative 2. All right. Okay, so now we're going to actually find dy by dx, and we'll do that by using the product rule. So brackets would help. 1 plus 1/2, so it's the derivative of the first bracket or function, negative 1/2, okay, times the second, x squared plus x to the negative 1 plus, okay, the first, x plus x to the half, positive half, of course, times 2x minus x to the negative 2. Okay, so it's long and ugly, but we're going to simplify that. Okay, so we would multiply and before I even do this, I wonder if we could maybe, no, I don't think we can. I was looking to see if there's anything that we could factor out, but in this case, we can't. Okay, so I'm going to do this the long way. So this times this is x squared, okay? The outer, which is plus x to the negative 1, the inner, which is 1/2 x. We're going to add the exponents. So then what we have is okay, and then the last, which would then give us the 2 last, and plus 1/2 x to the negative 3/2. Okay, and I'm simply just going to put the plus and not have a bracket, only because it is a plus. Okay, so the first 2x squared, the outer, so negative x. Be careful of all of your signs. Okay, so this is a 1 to the negative 1. Okay, and the inner, so x, 2x, 3/2. Okay, and then the last, which is minus x. Okay, so I think that's everything. Okay. All right, so the next step would be for us to collect like terms. I'll start with the highest, these two. So it'd be 3x squared. Okay, done those two. Then we'll do, I guess I probably should have done this one first. 1/2 plus 2. Okay, so over 2. My mistake, it should be 5/2. X to the exponent 3/2. Okay. Then we can do the negative. These two will cancel out, cancel each other out, and then we're left with, let's see, negative 1/2 x to the negative 3/2. Okay, so positive exponents. 3x squared plus 5/2x. 3 to the exponent 2 minus 1/2 x to the exponent 3/2. Okay, let's see. Can you see that? I'm going to fix that up for you. Okay, the exponent 3/2. Okay, so in this case, I would go back and make sure you've got everything. Okay, do I need to change that over to radicals? I probably should. Okay, but in this case, we're actually going to evaluate the slope. Okay, we're going to evaluate it, so you don't necessarily need to in this case, because you could just punch that into your calculator. But let's just do it for practice. dy by dx is equal to 3x squared plus 5/2 x square root by x cubed minus 1/2 x cubed. Okay, so that would be our final answer right there. It's completely simplified. And now what we want to do is evaluate the derivative at the point 1 and 4. So again, we just need the x, which is x is equal to 1. Okay, so dy by dx, when x is equal to 1, is equal to 3. And I just replace everything, everywhere there's an x, I put a 1. And you can see what I mean by, I didn't necessarily need to simplify, but we did it just for practice anyway. Anyway, that just works out to be 1. This also works out to just be 1, because 1 squared is just 1, and that of course works out to be 1 as well. So there we go, 1/2 and times 1. Okay, so we have 3 plus 5/2 minus 1/2. Okay, so 5/2 minus 1/2 is 4/2, which is just 2. So 3 plus 2 is equal to 5. Okay, and then dy by dx for x is equal to 1 is equal to 5. That means that our slope is equal to 5 at that point. Okay, so now we have everything we need. So we know that m at that point, the slope is 5, x is equal to 1, y is equal to 4. Okay, so again, we want y is equal to mx plus b, putting everything in. 4 is equal to 5 times 1 plus b. b then, rearranging everything, is 4 minus 5, b is negative 1. Okay, putting it back into the general equation, y is equal to 5x minus 1. Okay, and just for completeness, we're going to write a nice statement. The equation is y is equal to 5x minus 1. And that's your final answer. So one last thing that we're going to do today, and that will conclude our lesson, is you're going to check your learning. So this is more of an extended question, but I think you can handle it. What are the coordinates of the points on the graph of f at x is equal to x plus 1, x plus 2, at which the tangent is parallel to the line with the equation of 3x minus y minus 1 is equal to 0? Okay, I'll give you a little bit of a hint. Now you need to find the derivative, which will give you the slope of the tangent of this line, okay? And this line here, you just need to isolate y and turn it into slope-intercept form, okay? Compare the two slopes, and parallel lines have a characteristic feature about the slope. Okay, so make your decision. Okay, another color pen here. So the answer is C. Okay, and that concludes our lesson for today, and we'll see you next time.